Let's discuss expectation values and their relation to eigenvalues. Now in postulate 6, that tells us that the expectation value is derived from the classical value of the mean. We know how to calculate a classical mean for a continuous distribution, right? We just pop the operator omega hat in between the wave function and its complex conjugate, integrate over all space, and divide through by the normalization condition. The expectation value, right? It's the weighted average value that we would expect to get if we did an experiment, a proper experiment in the lab, and we evaluate that observable omega. Right. Now, if we prepare the system in an eigenstate of the operator, then the one and only value that we measure is the eigenvalue. And in this case, when the system is prepared in an eigenstate of the operator, the eigenvalue equals the expectation value. But if we prepare a system in a non-eigenstate of that operator, then we can get either a continuous or a discrete distribution. And continuous distributions and discrete distributions, they can either be symmetrical, such as this one, or they can be skewed, right? Like the Maxwell-Boltzmann distribution that we've seen and encountered many times before, right? Note that when you have a symmetrical distribution, the mean is equal to the most probable value. When you have a skewed distribution, then the mean will be different than the most probable value. In a discrete distribution, the mean value may not be one that you ever measure an actual value for, right? Because in a discrete distribution, you only measure certain values. Okay, but we can average over either one of those types of distributions. Now let's do an example. Do a calculation for a system placed in a pure state, an eigenstate of the operator omega. And we have a normalized wave function that describes this state, psi1, and it gives us then an eigenvalue omega1 when operated on by omega hat. Let's calculate what is the expectation value of omega hat when we do a correctly performed experiment. Okay, let's do the calculation. We know that this system, it's an eigenstate, psi1. The operator will return then an eigenvalue omega1. When omega operates on psi1, we'll get the value, a constant, a number, omega1 times the original wave function psi1. Now let's calculate the expectation value of this operator. We have to put the operator in between the wave function and its complex conjugate, divide through by the normalization constant. Oh, wait a second, we have normalized wave functions, so the denominator from our equation for the expectation value is just equal to 1. We'll leave that out here. When omega operates on psi1, we know what that equals. That equals omega1 times psi1, so we'll substitute that in here. We then recognize that omega1 is a constant. We can pull a constant out of the integral, leaving behind psi1 star times psi1, integrated over all space. That again is the normalization condition. This is equal to 1 because we had a normalized wave function, and so we get the trivial result. When we prepare a system in an eigenstate of the operator, the eigenvalue is equal to the expectation value. All right, that's just what postulate 1 predicted. When the system is in a pure state, the value of the observable is equal to the eigenvalue of the operator that corresponds to that observable. That's the one and only one value we get. Now let's do a little more complex example. The harmonic oscillator, our friend, the harmonic oscillator. We know the ground state wave function, and we know that it is an eigenstate of the Hamiltonian operator, the total energy operator. Total energy is kinetic energy plus potential energy. We know what those two operators are as well. So let's calculate the expectation values of the total energy, the kinetic energy, and the potential energy for the ground state of the harmonic oscillator. Familiar potential, that parabolic potential, when we get levels of constant energy, total energy, right, spaced by even amounts. But in the ground state, there is that 0 point energy of the harmonic oscillator. And so for an oscillator, or a pendulum also has this same type of potential, right? Then we have a particle here. It starts off, has 0 kinetic energy. It accelerates down until it reaches maximum kinetic energy and 0 potential energy before it decelerates back up and stops here. We'd have that oscillatory motion back and forth in the ground state, where you also have 0 point energy. Right? Doesn't go to 0 for the total energy. All right, now the total energy, the Hamiltonian gives us the total energy, sum of kinetic plus potential energies, right? And we know that the wave function is an eigenstate of the Hamiltonian, and therefore it will return the eigenvalue E naught for the ground state, or 1/2 h bar omega is the ground state energy. And so we've got the Schrödinger equation, which is an eigenvalue equation. When the operator, the Hamiltonian, acts on the ground state wave function psi naught, it gives us the energy E naught, a constant, times the original wave function. The expectation value, right? We put the operator between the wave function and its complex conjugate, divide by the normalization condition. Oh yeah, we have a normalized wave function, so this denominator here will be equal to 1. H hat acting on omega naught, that gives us E naught, right? And therefore we can substitute in E naught here, pull that out of the integral again because it's a constant, and therefore, yes, the expectation value of the Hamiltonian, the mean total energy, is equal to the eigenvalue 1/2 h bar omega. The operator was an eigenfunction. The wave function was an eigenstate of the operator, so we get that one and only one value. Now, let's calculate the expectation values of the kinetic energy and the potential energy. The formula is going to look very much the same type of formula there, but now we have to substitute in the appropriate operator for kinetic energy or potential energy. Which one of these should we calculate first? We don't have to calculate all three because we already have the total energy, and we know that the total energy is equal to the sum of kinetic and potential energy. So if we calculate any other one of these two, we can calculate the third by difference. And, well, the potential energy is easier to calculate because you're only going to multiply by an x squared, whereas you'd have to take a second derivative up here. So why don't we do the potential energy, right? Psi naught is not an eigenfunction of the potential energy operator. So now we're going to have to evaluate the integral explicitly, right? We need to put the operator in between the wave function and its complex conjugate, divide through by the normalization condition. This will be equal to 1. This we actually have to go evaluate through tables or from Mathematica, and that we can do. What we would find is the mean potential energy, right? The expectation value of the potential energy operator is equal to half the total energy. So if the potential energy is half the total energy and the kinetic energy can be found by difference, then sure enough the kinetic energy is also 1/2 the total energy. So for a harmonic oscillator, the mean values of the potential energy and the kinetic energy are equal. Anytime we do a measurement of the kinetic energy or the potential energy, we'll get a value, but these values aren't always the same. We get a distribution of values. The kinetic energy and the potential energy are constantly changing, but that's because there are not eigenvalues of the system. The total energy is constant. The kinetic energy and potential energy aren't, but their expectation value, their mean value, is always the same. The mean value is always half the total energy, right? But instantaneously, kinetic energy or potential energy, they are constantly changing and constantly giving us different values. So I hope this exercise has helped to clarify the differences between expectation values and eigenvalues. It's shown you how they're related to each other, and I hope as well that it's shown you when measurements yield one value as opposed to a as opposed to a distribution of values, even for a well-prepared system, a model system like the harmonic oscillator.